Hey guys, welcome back. It's week 11 here for 120, and this week we're going to focus on a new technique called hypothesis tests. Last week was all about confidence intervals. Hypothesis tests are also an important tool for statistical inference. It's really one of the two big tools. Confidence intervals and hypothesis tests are how we actually do statistical inference in the real world. So this week is going to be all about hypothesis tests, and we're going to do lots of hypothesis tests for the rest of the semester too. To establish the context a little bit, confidence intervals are all about estimation. Confidence intervals are all about estimating a population parameter based upon our sample result. Hypothesis tests, on the other hand, are tools for asking questions. Do we think this is true? Is there support for this claim? Are we justified in asserting blah? Hypothesis tests are the important tool for us to wonder, should we take action? Does it seem like there's evidence that something is going on here? What conclusion should we draw based on the sample result? And because of that, they're oftentimes the most important statistical tool that we use. One little note about this material, I think the first time you see a hypothesis test, there's a lot of information and it can be kind of overwhelming. But just like with confidence intervals, they all basically work the same way. And once you've got the big concepts down for hypothesis tests, it's easy to understand how to do different kinds of hypothesis tests. So hang in there. We'll do some examples today. It might seem like a lot at first, but once you've absorbed this material that we're talking about in the video today, you'll be ready for most of the material that we're going to cover for the rest of the semester. All right, so let's dive in. I think the easiest way to understand hypothesis tests are to think about criminal trials. Might seem kind of weird, but actually hypothesis tests and criminal trials are philosophically identical procedures. In fact, modern criminal trials derive from the same logical foundation that hypothesis tests do. And I think a lot of you guys probably have some intuition for criminal trials. Maybe you've seen a movie or a TV show that features criminal trials. So I hope that by connecting hypothesis tests to criminal trials, it'll help you understand what's going on. So first, I'm going to break this up into 4 important steps. Every hypothesis test that we do for the whole semester is going to have 4 important steps. Let's break it down. First, in a criminal trial, we wonder, is the defendant innocent or guilty? That's the big question. That's the reason we're having a criminal trial. We've got a defendant. We need to figure out if they're guilty or not. Now that's really similar to a hypothesis test. In a hypothesis test, the null hypothesis is the defendant. The null hypothesis, we call it H0 for short. That's H0 here. I say that out loud as H0. Not is an old-fashioned math word for 0, but people still use it all the time. The null hypothesis, H0, is on trial. The null hypothesis is always a statement about a population parameter. In the null hypothesis, we're going to make it clear what we think is going on with the population. On the other hand, there's got to be an alternate hypothesis. And the alternate hypothesis is the claim or question that we're investigating. In a criminal trial, we always assume that they're innocent until proven guilty. And we do exactly the same thing in a hypothesis test. In a hypothesis test, we assume by default that the null hypothesis is true. That's our statement about the population. But the real reason we're doing the hypothesis test in the first place is because we suspect that the null hypothesis is false. Just like a criminal trial, we assume that they're innocent by default. But the whole reason we're doing a criminal trial is because we think that they're guilty, right? That's why we wouldn't do a criminal trial if we thought they were innocent. But we need to establish that they really are. We assume innocent until proven guilty. In a hypothesis test, we assume that the null hypothesis is true, but we're actually looking to support the alternate hypothesis, HA. That's the thing that we're claiming about this population. That distinction might seem kind of weird at first, but we'll look at some examples and I know it'll become clearer for you, so hang in there. Okay, step 2. In a criminal trial, we have witnesses and evidence. People come up to the stand, they tell their story, they give their expert testimony, documents are reviewed, etc., etc. Those pieces of evidence collectively help us decide. In a hypothesis test, of course, we have sample data. We're going to use special sample statistics, called test statistics because we use them in a hypothesis test, to make a summary of all of the evidence that's presented by the sample. So of course, in stats, data itself is the evidence that we refer to. But evidence alone isn't enough to make a conclusion. We also need to make some sort of judgment call about how strong or not strong that evidence is. And that's step 3. In a criminal trial, lawyers make arguments, jurors might have discussions. People have to decide how strong this evidence really is and how convincing they find it. For us, in a hypothesis test, we use probability. Of course, that's why we just spent so much time talking about probability. We're going to use the likelihood or probability of a particular sample result occurring in order to make our decision about whether or not we're going to reject the null hypothesis. And that notion of probability in this context, it's got a special name. It's called a p-value. P-values are kind of a big deal. For some folks, historically, the p-value's been the only important part of the test. I hope I can change your mind about that a little bit, but it is a very important part of the test. There's a lot of confusion out there about p-values. So the very first thing I want to do is tell you the definition of what a p-value is, and this is so important. These probabilities, or p-values, are the probability of observing a sample result that's as or more extreme than the one we got, assuming that the null hypothesis is true. Kind of a big sentence to say, but every single word there is absolutely critical. P-values are the probability of getting a sample result like the one that we saw. What's the probability of having a test statistic like the one we got? Assuming that the null hypothesis is true. That's a really important assumption because we can't compute these probabilities unless we know something about the population. So we have to make we have to be clear about what underlying assumption we're making. Think about your z-score formulas. You need to know mu, you need to know p, those population parameters. For us, in a hypothesis test, that comes directly from the null hypothesis. We can't compute this stuff unless we're upfront about the assumptions we're making, of course. Actually finding these things are totally the same as the forwards problems that we did before for sampling distributions. Think back to week 8. That was the first week where we started doing videos in this class. Those forwards problems that we practiced are exactly what we're going to be doing here for the p-values. That's why we practiced them before. Those problems are just going to be a small part of a larger process that we're going to do in these problems. So you've already seen how to do those things. Don't worry, if you're feeling a little rusty, I'll take you through it in the video again today so you can see exactly what's going on. But I think it's helpful for you as you're learning and putting all the pieces together. Confidence intervals are backwards problems. These hypothesis tests, they're forwards problems. We're going to be computing probabilities for particular sample results. Okay, one more step. 4. 1, 2, 3, 4. All of these things have 4 steps. I like to label them when I'm working through them personally. I'll do that for you guys too to help you keep it straight. So in a criminal trial, back to criminal trials, we wonder if they're innocent or guilty. The witnesses came to the stand to present the evidence. The lawyers argued about it. The jurors debated about it. But finally, ultimately, we need to make a decision about the defendant. And that's what step 4 is, the conclusion. What do we actually think now? We review the evidence. Do we think they're innocent or guilty? In a hypothesis test, we're going to make that decision based on the p-value, because that's how strong our evidence is. And specifically, we're looking to see if the p-value is small enough. Small p-values are evidence against the null hypothesis. That might not seem immediately obvious. Let's think about why that's true. And I think, this is so important. This is just like this issue of why small p-values matter is the whole crux of hypothesis tests. It's kind of deep, but we'll think about it a lot together. So here's the reasoning. If the p-value is small, that means our sample result is very unlikely according to the null hypothesis. Remember, these p-values are probabilities. It's the probability of getting a sample result like the one we got. But in order to compute them, we have to assume that the null hypothesis is true. If we make that calculation and find out that according to the null hypothesis, our sample is very, very unlikely, then we have kind of a decision to make. It seems like, well, either there's something wrong with the sample data or there's something wrong with the null hypothesis because they don't agree. If the p-value is small, the data and the null hypothesis don't agree. So if that's the case, we, of course, are going to go with the actual real-world data that we found. That's what empiricism is all about. That's what this whole science thing that we're doing is all about. We made these observations. We're going to use those as the foundation for reality. If our actual observations disagree with our hypotheses, then we've got to reject those hypotheses. And that's how these things work. Small p-value means reject the null hypothesis. Small p-value means reject the null hypothesis. That's how these tests work. So because of that, every hypothesis test ends in one of 2 ways. If p is small, then we reject the null hypothesis. Otherwise, if p is large, we didn't find the evidence that we're looking for, and so we failed to reject the null hypothesis. Speaking of, that reminds me, it's time for the answer to the secret video question. The answer for today's secret video question is Play-Doh. Play-Doh is the answer to the secret video question for week 11, video 1. I love Play-Doh. I love how Play-Doh smells. I think it's the best stuff ever. I totally just stock Play-Doh in our guest bedroom is like my office, especially now. And I'm looking at my stash of Play-Doh up there. Sometimes when I'm thinking and I just want to space out, grab a ball of Play-Doh and play with it. Okay. Back to p-values. One thing you might be wondering, hey, wait a second. We reject if it's small. We reject the null hypothesis if the p-value is small. Well, how small is small? The answer is, it's totally up to us. This notion of how small is small enough, that's actually something that we have to decide. And it's got a special name. It's called the significance level. And the symbol that we use for it is alpha, like the Greek letter A. It looks like a little fishy if you write it out. We're looking for a p-value to be smaller than this cutoff, this significance level cutoff. If it's smaller than that, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. And generally speaking, in lots of literature and lots of different disciplines, folks use alpha equals 0.05 by default. So in other words, if there's less than a 5% chance of observing a sample result like the one we got, then we're going to reject the null hypothesis. That cutoff, alpha equals 0.05, that's totally arbitrary. We could use alpha equals 0.01, we could use alpha equals 0.001. Later, next week, we're going to talk about error types and hypothesis testing. Those have a big impact on what we choose for alpha. But generally speaking, if the problem doesn't specify a specific significance level, then we're always going to use alpha equals 0.05 by default. If you're taking a quiz and the problem doesn't tell you what alpha is, you can always safely assume alpha equals 0.05. All right, that was a lot of information. And there's still some important details there that we need to talk more about. But before we do, let's actually do a couple of examples of these things. I think if you can see some real examples, you'll get a better understanding for how height tests work. So here is our first example. Just like the other examples we're going to do in this video, this is about a proportion. We're doing a test for P, population proportion. We are investigating a claim about the population proportion, and we're going to use sample data to make our conclusion. So here's the setup, and this is real sample data, by the way. I really like this example. In fall 2015, here at Denison, I was still teaching this class. My stats class had 16 female students out of a total of 24 students. Maybe just to make a little note about that, that means p hat is equal to 16 out of 24. We've got a sample proportion there. And let's say, based on this sample result, I suspect that the gender ratio at Denison is greater than 50% female. At the time, and still now, that was true, by the way. That semester was particularly dramatic. That semester, the gender ratio was 57% female. It's changed. But it really was the case. But does this sample result support my claim? This sample that I saw, does it support my claim or my suspicion that more than half of students at Denison are female? Well, let's investigate. Let's perform full hypothesis test, and we're going to use alpha equals 0.05. Here we go. All hypothesis tests have 4 steps, 1, 2, 3, 4. So I'm going to do them in that order. I'm always going to label them. First, we need hypotheses. We need hypotheses for this stuff. What are the hypotheses? I've got to have two. I know I need a null hypothesis, and I need an alternate hypothesis. Every hypothesis test has those two things. Remember, the null hypothesis is the assumption that we're going to make in order to compute the p-value. But the alternate hypothesis is the claim or the suspicion or the question that we have about this particular population. And I think because of that, the alternate hypothesis is the easiest one to write first, because it's right there in the problem. Here, on this one, it says, I suspect that the gender ratio at Denison is higher than 50% female. That's my claim here. That's my suspicion. I'm trying to find evidence to support this assertion. So that's got to be the alternate hypothesis. I think that the proportion P is greater than 50%, 0.50. Let me just annotate that. We think proportion of female students is greater than 50%. That's what I'm asserting, or I hope to show about this population. But remember, just like in a criminal trial, it's always innocent until proven guilty. I have to be honest about the baseline assumption about the population. So here, that's got to be p equals 0.5. Assume by default that there's not an imbalance. So that's how hypotheses work. I think it's easier to write the alternate hypothesis first, because that's the claim or the suspicion in the problem. The null hypothesis always has to be a statement of equality, innocent until proven guilty. And because of that, it always works this way. In the alternate hypothesis, it's always an inequality, either less than or greater than or just straight up not equals to. The null hypothesis always has an equal sign. The null hypothesis always has an equal sign, because here's where we're telling what our default baseline assumption is about the population. This is the status quo. This is our prior assumption. Here's what we'll assume by default. This value, p equals 0.5, is going to be the thing that we use when we compute the p-value. Okay, cool. So there's our hypothesis. Moving on, we need a test statistic. And all this is a z-score. The test statistic is just a z-score. That's why we've been talking about z-scores all semester, because they're the basis for how we do these hypothesis tests. We are going to summarize our sample data using this z-score. And let me remind you how these things go. This, if you've forgotten how these work for sample proportion, for p-hat, you might want to review the problems that we did in week 8, because we found some z-scores there in week 8. I'm going to talk through it again now, but if it still seems confusing, go back and review those problems. You all did really well in the quiz on those problems, so I know you understand them. Go back and look at those things and see how this stuff goes. If you're still feeling confused, of course, come talk to me during office hours. It's always the case that z is equal to observed minus expected divided by the standard deviation. That's every z-score. In this context, for our observed, that's p-hat, the sample proportion. That's the actual data that we saw, and ours is 16 out of 24. That's the thing that we actually saw in this real-world sample, my stats class. Our expectation, of course, has to be the population proportion. Here, that's coming directly from our hypotheses. We're going to assume the null hypothesis is true, that p is equal to 0.5. For the standard deviation, we're going to use the formula for p hat. Again, if you can't quite remember this, go take a look at the week 8 notes, it's all there. But it's the square root stuff. Square root 0.5 times 1 minus 0.5 over my sample size is 24. That's the standard error. In other words, the standard deviation for p hat. So let's stick it in the calculator and find out. That's 16 over 24 minus 0.5 divided by the square root 0.5 times 1 minus 0.5 divided by 24. Let me just pause. And does this all look good? Yep, all looks good to me. We've got a test statistic of 1.63. That's the z-score for this data. Okay, cool. Well, let's use the z-table to find out how likely this is. For our p-value, this is the probability of getting test value, or a sample result, as or more extreme, assuming that p equals 0.5. And we've already got the z-score for this thing, so we need to find what's the probability that z is bigger than or equal to 1.63. That's what we're looking for here. What's the probability of getting a sample result that's as or more extreme than this? We found the test statistic. Let's look it up in the z-table. One little note here that I'll talk more about when we do more tests. I'm doing greater than, that's my notion of extreme, specifically because that's what the alternate hypothesis test shows. The alternate hypothesis. Did you follow that? That was really important. I know this one has to be bigger than because my alternate hypothesis is bigger than. We're wondering if it's bigger than 50%. So we're looking for the probability of getting something that's big. In other tests, we might do less than also. Okay, so let's take a look at the z-table. Oops.